All right, so picture this. You've got this sewing needle, right? And you want to spin it around like a full 180. But here's the catch. You got to do it in the absolute tiniest space possible.
Yeah, it sounds kind of like a party trick gone wrong or something.
Right. But actually, believe it or not, this kind of silly image is actually at the heart of a pretty deep mathematical puzzle, one that's been bugging mathematicians for like over a century. It's called the Kakeya Conjecture.
Yeah, the Kakeya Conjecture. And that's exactly what we're going to be digging into today.
We are. We're going to be trying to understand, a pretty major development in this long-standing problem. Specifically, we're talking about its solution in 3 dimensions. So, buckle up.
Yeah, get ready for some pretty cool geometry.
Absolutely. And we've got some really fascinating sources for this deep dive. In particular, there's this recent research paper, what they call a preprint, by a couple of professors, Hong Wang from NYU and Joshua Zahl from the University of British Columbia.
Yeah, and just to be clear, for anyone who might not be familiar with the term, a preprint server, it's basically like, think of it as a platform where researchers can share their findings, their papers, before they've gone through the whole official peer review process.
Right.
Like before it's been like officially published in a journal. So it's kind of like, getting a sneak peek at the cutting edge of research.
Absolutely.
And this particular preprint has been making some serious waves in the math world.
Yeah, big time. And, to really appreciate just how significant this is, we're talking about a problem that has obsessed some of the biggest names in mathematics, people like Terence Tao. He's a Fields Medalist. That's basically, the Nobel Prize for math. He's called this resolution one of the top mathematical achievements of the 21st century. So that's saying something.
Yeah, that's huge. And Eyal Libesky, he's the chair of mathematics at the Current Institute. He's also called it a major breakthrough. So we're not messing around here.
No, we are not. We are diving into some deep waters. So for you, the listener, think about it this way. The Kakeya Conjecture, it's really about exploring this fundamental question about space and direction.
Yeah.
Like, how much room do you actually need for something? Like, say, our imaginary needle, to be able to point in absolutely every single direction you can imagine.
Right. What's the absolute minimum? Should it be almost nothing?
Yeah. Could you squeeze it down to practically zero space? That's kind of the mind-bending idea at the heart of this whole thing.
It's a real head-scratcher. And to really understand how we got here, we need to go back to the beginning.
Back to the very beginning. So this whole mathematical journey, it all started back in 1917 with a Japanese mathematician named Sōichi Kakeya. And his original question, it wasn't actually about our 3D world, the one we live in. It was actually about a flat surface, like a piece of paper, a 2-dimensional space. He was wondering about the smallest area you would need on that flat surface to rotate a needle 180 degrees. Think of it like this. You're tracing the path of the needle as it spins around. What's the smallest possible shape you can make?
Yeah, what's the absolute minimum area that shape has to cover?
Exactly. And these shapes on the flat plane, the ones that let you rotate a needle like that, they're called Kakeya needle sets. So you can kind of picture the needle sweeping across a certain area as it turns. And that area, that's a Kakeya needle set in 2 dimensions.
Right. It's the set of all possible positions that needle can occupy as it rotates.
Now, fast forward a bit, and mathematicians being, mathematicians, they started thinking, okay, what if we take this idea off the flat plane and bring it into our 3-dimensional world? What happens then?
Yeah, what happens in 3D?
And that's where the Kakeya set conjecture comes in. It's basically the same idea as these 2D needle sets, but now we're not talking about area anymore. We're talking about volume, the actual space something takes up.
Right. The 3-dimensional version asks, what's the smallest space, the smallest volume that you need in order for a needle to be able to point in every single direction you can think of.
Yeah, every single direction in 3D space. Up, down, sideways, diagonally, you name it. Could you have a set, a shape that lets you do that, but takes up almost no space at all? That's what they wanted to know.
And this is where things start to get really, really interesting. Because the conjecture basically grappled with this, this kind of wild idea.
Wild, yeah.
Could such a set, one that lets you point a needle in every direction, actually have zero volume?
Literally take up no space.
Yeah, it sounds kind of crazy, right? How can something that lets you point in every direction not take up any space at all?
It's like a magic trick or something.
Right. It's a real paradox. And for decades, this is exactly what mathematicians have been trying to figure out.
They've been racking their brains over this. And now, this new research by Wang and Zahl, it claims to have finally cracked the code. They say they've solved it.
Yeah, they've come up with a definitive answer.
So spill the beans. What's the big revelation? What did they find?
Well, the core finding is this. Wang and Zahl have proven that Kakeya sets in 3 dimensions. While they could theoretically approach zero volume in a certain mathematical sense.
Okay, wait, hold on. Approach zero volume, what does that even mean?
Okay, so think of it like this. You've got a shape, right?
Eh.
And you're kind of squeezing it, making it thinner and thinner in some directions, but it still exists in 3D. It's still a 3-dimensional object.
Okay, I'm kind of visualizing it.
So they're saying that even though you can kind of, squish these Kakeya sets down in certain ways, they can never truly have zero volume.
They always have to take up some space, no matter how small.
Right. They have to occupy actual 3-dimensional space.
Yeah.
They can't be squashed down to be essentially 2-dimensional or 1-dimensional.
Okay, so it's like there's a fundamental limit to how much you can compress these things.
Exactly. And that's the resolution of the conjecture. They've proven that, yes, Kakeya sets can get really, really thin, but they could never completely disappear. They always have to have some 3-dimensional presence.
Wow. Okay, that's pretty mind-blowing. So, I'm guessing the math world is pretty excited about this, right? I mean, it sounds like these aren't just, minor tweaks to our understanding. This is like a fundamental shift in how we think about space.
Oh, absolutely. It's a huge deal.
Yeah.
Guido de Filippis, he's a mathematician at the Current Institute. He called it a wonderful piece of mathematics. He emphasized that it builds on decades of work by so many mathematicians, and that it's really elevated our understanding of this incredibly complex geometric problem to a whole new level. He's actually optimistic that this work, their insights, will pave the way for even more breakthroughs in the future.
So it's like, it's not just an answer, it's opening up new doors, new possibilities.
Exactly. And we also heard from Pablo Schmerkin. He's a mathematician at UBC, and he pointed out something really fascinating. He said that when you first hear about the Kakeya conjecture, it sounds so simple, right?
Yeah, just a needle pointing in different directions.
Right, but it's actually incredibly deep. It has all these surprising connections to other areas of mathematics, like harmonic analysis and geometric measure theory. These are pretty advanced fields.
So it's like this simple question about a needle leads you down this rabbit hole into this whole world of complex math.
Exactly. And what's really impressive, what Schmerkin highlighted, is that Wang and Zahl, they didn't just solve the Kakeya conjecture, they actually figured out this more general principle about how these things called tubes intersect in space.
Okay, hold on. Tubes. Now we're talking about tubes. What are these tubes? Are we, like, plumbing now?
No, not exactly. I mean, you can kind of visualize them as these long, thin, cigar-shaped regions.
Okay, like a bunch of cigars floating around in space.
Yeah, something like that. But in this mathematical context, these tubes, they're more of a concept that mathematicians use to analyze how things are oriented in space, how they point in different directions.
Okay, so it's like a way of representing directionality.
Right. And proving the Kakeya conjecture, it really depends on understanding how these abstract tubes intersect with each other in 3-dimensional space. So, even though they're abstract, it can help to kind of picture them as these, long, thin objects moving around and bumping into each other.
Okay, I'm trying to wrap my head around this. So why are these tubes so important? Like, what's the big deal about how they intersect?
Well, if we zoom out a bit, and this is something Guido de Filippis emphasized, this whole thing isn't just some quirky math problem with no real-world relevance. Understanding how these tubes interact, it actually has some pretty significant implications for other fields, like harmonic analysis and number theory, even areas like computer science and cryptography.
Whoa, whoa, whoa. Computer science and cryptography. How does a needle pointing in different directions relate to computers and codes?
Yeah, it might seem kind of out there, but think about this. In a lot of problems in computer science and cryptography, the information that matters, it can actually be represented as these things called wave packets. And mathematically, these wave packets, they can be thought of as being concentrated on these tiny tubes in some kind of abstract space. So if you want to understand how these packets of information interact with each other, you need to understand how these tubes intersect.
Okay, so it's like the tubes are kind of like the pathways for information.
Yeah, something like that.
Yeah.
And understanding how they crisscross, it can help us develop more efficient algorithms or come up with new ways to encrypt data.
So this is fundamental stuff. This is the underlying architecture of how information works.
Exactly. It's about understanding the basic building blocks of how information moves and interacts in these complex systems.
So this research by Wang and Zahl, it's basically giving us a much clearer picture of how all this works.
Exactly. And it's not just about those specific fields. It's about building a deeper understanding of the structure of space itself, how things are oriented, and how they interact.
So this is kind of like understanding the laws of physics, but for information.
Yeah, I like that analogy. It's about uncovering the fundamental rules that govern how things work at a very deep level.
Okay, so listener, you're probably thinking, all right, that's all well and good, but why should I care about this? This is some pretty abstract stuff.
You're right, it is abstract. But here's the thing. This breakthrough, it represents a fundamental insight into the nature of space and direction. And that kind of understanding, it often has ripple effects across all sorts of fields, even ones that seem completely unrelated to pure geometry.
So like even if you're not a mathematician, this stuff could still end up having an impact on your life in ways you might not even realize.
Exactly. It's like, think about the laws of physics again. You might not be an engineer, but those laws still govern how the world works, how buildings stand up, how cars move. This is kind of like that, but for the mathematical universe.
Okay, so to sum it all up, the Kakeya conjecture in 3 dimensions, this problem about the smallest space you need for a needle to point in every possible direction, it's been solved by Professors Wang and Zahl. They've shown that even though such a space might theoretically have 0 volume in a very specific mathematical way, it actually has to occupy 3 dimensions. You can't cheat geometry, basically. Fully exploring 3D space requires a 3D object no matter how thin you try to make it.
Yeah, that's a great way to put it. And the math world is really buzzing about this,
Yeah.
It's a huge accomplishment. It's the result of decades of work, and it's opening up all these exciting new avenues for research.
Yeah, it's like a whole new chapter in the story of geometry. And
Yep.
who knows what we'll discover next.
Exactly. The possibilities are endless.
Oh. So here's a final thought for you, listener, to chew on. Think about how these seemingly abstract mathematical concepts, things like the Kakeya conjecture, can actually lay the groundwork for advancements in all sorts of fields, even fields that seem completely unrelated to pure math.
Right. Who would have thought that a question about a spinning needle could have implications for computer science and cryptography?
Exactly. It just goes to show, you never know where curiosity will lead you and what other fundamental questions are out there just waiting to be answered that might have unexpected and amazing implications for the future.
That's a great question. I guess we'll have to wait and see.
Yeah, the journey of discovery continues. Thanks for joining us for this deep dive into the Kakeya conjecture. Until next time.
See you then.